Hello everybody, this is 2021 AIME II problem number 13, and here's a view of this number theory problem. So we would like to have this expression divisible by 1000. So in the language of modular arithmetic, that's equivalent to saying that 2 to the n plus 5 to the n minus n is congruent to 0, or I can simply move the n to the right hand side. So that is congruent to n modulo 1000, but by Chinese remainder theorem we can turn this into a system of congruences where 2 to the n plus 5 to the n is congruent to n modulo, well, because 1000 is just 8 times 125, where 8 and 125 are relatively prime. That modulo 125. All right, so that's pretty much what the question is asking. So find an n which satisfy both of these congruences simultaneously. I think when you look at these two, you would probably realize that modulo 8 is probably the easier one. Modulo 125 will be slightly harder because exponential forms, trying to make the calculations modulo 125 is significantly more cumbersome. All right, so let me just go ahead and say that this is congruence 1. And this one is congruence 2. Before I also begin, do you guys agree that because 8 is 2 cubed, and there's a 2 to the n on the left hand side, 2 to the n will be congruent to 0 modulo 8 if n is greater than or equal to 3. Similarly, 5 to the n modulo 125 is congruent to 0 if n is greater than or equal to 3 as well. So the whole system will reduce significantly if n were not 1 or 2, basically, right? So we are looking for a positive n. So, but obviously n cannot be 1 or 2. For instance, if you plug in 1 in the first congruence, 2 plus 5 is not congruent to 1. So 1 definitely fails the first congruence. It also fails n congruent to 2 also fails, or n equals 2 also fails the first congruence as well. We don't even need to check the second congruence, right? 2 square is 4 plus 5 square is 25. 4 plus 25 is 29. 29 is not congruent to 2 modulo 8, right? 29 is congruent to 5, I believe, modulo 8. Do you guys agree? So for the rest of the problem, since, okay, let's write this down. Since n equals 1 or n equals 2 is not a solution, then we can reduce this system of congruences in the following way. So let me write it like this. Well, 2 to the n will be just 0 for n greater than or equal to 3. We can reduce to n greater than or equal to 3, in which case the first congruence suddenly becomes 5 to the n is congruent to n modulo 8. And the second one, in that case, 5 to the n is divisible by 125 for n greater than or equal to 3. So we have 2 to the n is congruent to n modulo 125. Yeah, I just wanted to start with this observation to begin with because it makes life much easier. All right, so this is kind of like the revised congruences. So if you want, we can call them 1 prime and 2 prime. Do you guys see that? So that's the congruences I want to check. Okay, obviously 1 prime is much easier than 2 prime. So if you check 1 prime, so we want to find an n, find n. Oh gosh, so this color is very too much strong. Yeah, I don't want this color. Edit properties. Yeah, it's okay, there you go. Softer color is better. So what did we say? Oh, okay, so find an n for which, oh my goodness. All right, so this is insisting. All right, find an n for which 5 to the n will be congruent to n modulo 8. But come on, modulo 8 is, there's only 8 residues. You can quickly check all 8 of them, which one works and which one doesn't work. For instance, n equals 0 doesn't work. 5 to the 0, which is 1. 1 is not congruent to 0. 5 to the 1, is it congruent to 1? No. 5 squared, which is 25. 25 is just 1. 1, is it congruent to 2? No. It turns out that the order is 2 here, right? So which is pretty good. So and so on. So you guys will just see that it is 5 to the 5, because 5 to the 5 is just 5 times 5 to the 4. 5 to the 4 is just 1. So 5 is congruent to 5. Yeah, so this implies that n better be congruent to 5 modulo 8. Wow, that one was very, very easy, actually. Do you guys agree? So that's the solution to the first congruence. Now the second one. The second one is more kind of it requires a little bit more work. So for the second one, again, 2 prime, so we need to find an n which will satisfy the following. Well, when I say find an n which satisfy this, because by Chinese remainder theorem both of these must be satisfied at the same time, we already know some properties of n. N already satisfies this property. If we need it, we can make use of it, right? So we don't have to independently think of that second congruence, and then we can keep building on top of it. But along the way, we should be also careful, because suddenly you can find yourself significantly bashing stuff, right? So for instance, from here you can already plug in things like 5 plus 8L, and then that can cause us a lot of trouble as well. I think I was saying that don't get tempted to just directly plug this into this expression and solve it for L, because then suddenly you will see that it is going to make it bashier and bashier. So it turns out there's a way, like nicer way, to a very clean way, as DJ Madman on his AOPS post he mentioned. We are not gonna be tempted by plugging in things and then solving it pure bash, because we want n to be congruent to 2 to the n modulo 125. So that is equivalent to, when you think about it, the only way we can solve this thing is to first of all understand what n is in the numerator, modulo phi of 125. Do you guys agree? So let me just open a kind of like an imagination box here. So where phi is the totient function, do you guys agree that, for instance, 2 to the phi of 125 is congruent to 1 modulo 125? This is true by what? By Euler's theorem. But but we already know phi of 125 is just phi of 5 cubed, and that is just 5 cubed minus 5 squared, I should say. And that's just 125 minus 25, that's 100. So if I want to solve this congruence, I need to somehow evaluate n modulo 100, so that I can plug it in the exponent. Do you guys see that? So calculating n modulo 100 is, I can, using Chinese remainder theorem again, I can split it into n congruent to, find what n is congruent to modulo 4, and find what n is congruent to modulo 25. Do you guys agree? So suddenly, starting with modulo 125, we realize that we need to reduce it to modulo 25. We already know what n is modulo 4, right? So from here, n is congruent to 1 modulo 4. So I'm not concerned about the 4 part. So I still need n to evaluate n modulo 25. But think about it. This expression is true for modulo 125, so it must be true for modulo 25 as well. So that can kind of give me an idea on how I can calculate the value of n modulo 25. Do you guys agree this is true? So what I'm saying is, if this congruence 2 to the n is congruent to n modulo 125 is true, it must also be true that 2 to the n is congruent to n modulo 25. As an example, so for instance, this expression here is just 2 to the n minus n is equal to 125, say for instance k times k, and it's easy to just factor out a 25 here, and then so you still have a 5k inside of it. You can relabel it if you want, 25, say m for instance, times m. So 2 to the n minus n is congruent to 0 modulo 25. So this thing is true. The same thing for modulo 5 as well. You could have, instead of 25, you could have factored out the 5 instead. Do you guys agree? So what it tells us is, if you want to compute this modulo 25, again, check this out. So I need to know the value of n for this exponential form, but We know by Euler's quotient, or Euler's theorem, I should say, again, that 2 to the power phi, so this is both from Euler, right? So Euler theorem tells us that 2 to the phi 25 is congruent to 1 modulo 25, but where clearly phi of 25, the number of numbers less than or equal to 25 which are relatively 25 is just 25 minus 5, that's just a 20. Aha! So after all I need is the exponent modulo 20. But again, modulo 20 is just 4 times 5. I already know what it is, modulo 4. All I need is modulo 5. But wait a second, modulo 5, I need n modulo 5, right? But this expression is still true modulo 5 as well. So basically I have this kind of approach, kind of, it's like an algorithm in a sense. We especially use this technique. I used the similar technique in 2018 in my solution to 2018 AIME 1, I believe, problem number 11. You can check it on my YouTube playlist. We will do gradually, so we will start from here, but we know our direction. We will go here and then ultimately attempt our own problem. So let's start with modulo 5. Let me remind you. So modulo 5, so we have we know that n is just congruent to 2 to the n, like we said, because if n is congruent to 2 to the n modulo 125, it has to be congruent to 2 to the n modulo 5 as well, right? Okay, so I don't have to put the modulo sign again. But like we said earlier, because 2 to the 4, okay, maybe I didn't say it, so let me say it right now if I didn't. 2 to the 4, this one is from Fermat's Little theorem, right? Modulo 5 by Fermat's Little theorem. So that's the one that I'm going to use. All right, so therefore 2 to the, well, n is congruent to 1 mod 4, which means this is 1 plus 4k. Do you guys agree? So I am just putting it here. Oh, I'm so sorry for the sound. Okay, so, and this is just what? This is just a 2 modulo 5, like we said. So we are analyzing it modulo 5. Hey, n is congruent to 2 modulo 5. Now remember, we are going to go to the next level now, but before I go to the next level, let's think about it. I know that in the next level, because there's an n on the exponent, 2 to the 20 is congruent to 1. I also know that from this one. In that case, we have the following, because I know that I will need like modulo 20 in the exponent. Let's think about it. So we know that n is congruent to 1 modulo 4, and now we also know that n is congruent to 2 modulo 5. Aha! So combining these, again, Chinese remainder theorem, or just straightforward. So this is just 17, or you can just say minus 3 modulo 20. Now we can go to modulo 25, right? So modulo 25, again, we already know that n is congruent to 2 to the n modulo 25, but now remember, by expressing it in terms of modulo 20, so for instance, I can write it as, I can replace n with, say, for instance, minus 3 plus, I used k already, so let's use it L again, I guess, this time. So which is, okay, so I can write this as follows. I can write it as 2 to the minus 3. Do you guys agree? And then times, just like the same spirit here. I mean, I skipped a few steps there, but okay, so let me, if you guys want, so this is 2 times 2 to the 1 times 2 to the 4k, but I can write it like this. 2 to the 4 modulo 5 previously was just, is just a 1, right? So that's why this came out as a 2 modulo 5. All right, there you go. And this is 2 cubed to the minus 1. 2 to the 20, like we said, by Euler's theorem is just a 1. So this is times 1 to the L. So you get 8 to the minus 1, basically. Aha! So all you need is the multiplicative inverse of 8 modulo 25. So which means, what is the inverse of 8? Multiplicative inverse of 8 modulo 25, and if you investigate, you'll see that it is minus 3. Why? Because minus 3 times 8 is minus 24, which is just, if you add 25 to it, it is just 1 modulo 25. Okay, that makes sense. Okay, so kids left, so no more distraction. Where was I? Okay, so we just found that n is congruent to minus 3 modulo 25. yeah, this was modulo 25 apparently, right? So that's, so we are now one step away from finishing the problem. So far, because I now know that for the last case I will need to solve this congruence, so therefore in the exponent I would have to evaluate n modulo 100, and because Euler's theorem here, so far what we know is modulo 100, so I will need n evaluated modulo 4 and modulo 25. I already know modulo 4, this is a 1, and modulo 25, this is a -3. We just calculated it a minute ago. So you guys now can combine this, and finally n is congruent to, this happens to be also -3 modulo 4, right? So therefore this is just -3 modulo 100. Nice. Finally, modulo 125, we are ready to attack the original problem. Let me highlight the original, well, one of the two congruences that we started with. So we needed this one, right? All right, so let's do it. So modulo everything afterwards is just modulo 125. Whoops. So far we, okay, so this is given to us, n is congruent to 2 to the n, but that is 2 to the, replace n with -3, so this expression here, -3 plus, okay, so which letter should we use? Let's use m. 100m, right? That's what n is, which is again 2 to the -3 times 2 to the 100m. Let me put the m outside, but 2 to the 100 by Euler's theorem is just a 1, so this is just 2 cubed to the -1 times 1 to the m. 2 cubed is just 8. Oh, multiplicative inverse of 8. That's it. Modulo 125. That's it. That's the answer. So whatever is the multiplicative inverse of 8, that's what n must be congruent to modulo 125. Now, unlike the previous one, which was very straightforward to calculate the multiplicative inverse of 8, this one requires a little bit of work. You guys can, for instance, if you remember Euclidean algorithm, you guys can use Euclidean algorithm, the steps, to quickly find that number. Okay, let me, if you guys want, somewhat unrelated, but let's just do it so that we have a complete solution at least. 125 is equal to, not congruent to, equal to, well, by the division algorithm. Remember, Euclidean algorithm is just what? Repeated division algorithm. So all we do is we carry these two numbers, the quotient, not the quotient, the divisor and the remainder, and we reapply the whole algorithm, right? So let's just do it. So 8 is equal to 1 times 5 plus 3. 9, the next step, we're gonna move the 5 and the 3 one layer, right? So 5 is equal to 1 times 3 plus 2. We need to repeat this this process until the remainder is 1. That's what the Euclidean algorithm tells us. So it's still a 2, so we need one more step. 3 is equal to 1 times 2 plus 1. Oh, thank goodness. So stop. So that means 1 means stop the process. Now that we stop the process, we need to reverse engineer everything. So we need to write 1 as, so this 1 over here as 3 minus, so move that to the left hand side, 1 times 2. Now remember that 2, the previous remainder, so as a result I can replace it with that expression. 1 times the 2 is replaced with 5 times, sorry, 5 minus 1 times 3. That's a times, believe it or not. All right, there you go, which means this is equal to, so there's 1 times 3 here, there's another 1 times 3, so we have 2 times 3 minus 1 times 5. All right, getting closer. So this is equal to 2 times, wait, the 3 is just 8 minus 1 times 5 minus 1 times 5, so this is 2 times 8 minus 2 times 5 minus 1, so minus 3 times 5. All right, never gonna shoot another video outdoor again. This is annoying. All right, 2 times 8. Okay, so keep that 2 times 8 minus 3 times, replace the 5 with this one, so which is 1, 2, 5 minus 15 times 8. Oh, thank goodness. All right, so this is equal to, so 2 times 8 minus minus, so plus 15 times 8, so that is oh sorry, there's also a 3 here. Minus 3 times minus 15 is minus, sorry, 45 plus 2, 47. 47 times 8 minus 3 times 125. And it's easy to check with a calculator if 47 times 8, if you subtract 3 times 125, to see if it is equal to 1. All right, now we can go ahead and evaluate this modulo 125. Modulo 125, 1 is 1. 47 and 8 are just what they are, but then 125 modulo 125 is just a 0. That term just drops. So that's what it comes out to. Do you guys see that? Oh, so after all, the multiplicative inverse of we needed the multiplicative inverse of 8 up there, so it is 47 after all. So this number, so this implies we started with an n is congruent to just 47, I suppose, right? Multiplicative inverse of 8, which is 47, 125. That's it. So therefore, just to summarize what we did and to wrap up our solution, so we needed an n, which is earlier, you remember, maybe I need to highlight the stuff that we got. So we know that n must be 5 modulo 8. So that's the solution to the first problem, or prime 1. But at the same time, now we have a second problem, this one, the second congruence. The solution to this also, we have it now, and that's this. Now it's time to write them together and solve them simultaneously, which is, I mean, this part is also straightforward. So n is congruent to 5 modulo 8. At the same time, n is congruent to 47 modulo 125. And so what is the value of n, which we'll do? This is, if you memorize Chinese remainder theorem procedure, you can just use it directly. If you didn't, like me, it's annoying, but okay, so we can do it. So the answer must be one of these. It's either 47, or it is 47 plus 1 times 125, or it's 47 plus 2 times 125, and so on. Dot, dot, dot. 47 plus, I think 6 times 125, or 47 plus 7 times 125. So Chinese remainder theorem tells us that one of these is the solution, right? Either 47, well, 47 doesn't work right away. We can see that it doesn't satisfy the first congruence, right? So, but all of these satisfy the second congruence. Among these, only one of them will satisfy the first one, right? So we know this because we have an arithmetic progression. And yeah, so if you so only one of them, exactly one of them, will satisfy. If you do the algebra, you realize that it is this one. 6 times 125, 2 times 250, 750, 797. I think that's the smallest n, which will satisfy both of these congruences simultaneously, and that solves our problem.